So far, we have discussed a few solutions that were of Navier-Stokes equations, in which we made some certain assumptions and some simple models of the fluid flow problems, in which we tried to solve the Navier-Stokes equation analytically. You know, since these equations are non-linear in nature, it is very difficult to solve them analytically and find out a complete solution. The complete solution remains unsolved till today if we consider all the variables that are involved in those equations. So we considered a few equations, few problems in which the motion considered was of a steady nature. That is, we tried to simplify problems, and in one of those, the one parameter that we tried to ignore was by choosing the motion that was steady in nature. From that, it is obvious that the motion would not change with change in time, and therefore t will vanish, or we can ignore the variation due to time. One can imagine that if we add more parameters, more variables, and we take them into consideration of our fluid flow model, then it will make the situation that much more complicated. However, one has to deal with it, and even some exact Navier-Stokes equation are available even in certain simplified versions of fluid flow models. One such model is sudden motion of an infinite plate in the horizontal direction. So we consider the problem which involves sudden motion of an infinite flat plate. We defined a problem first. Consider a viscous Newtonian fluid on top of an infinite flat plate, as we said, lying in an xy plane at z equal to 0. The fluid is at rest until the time t0, or in other words, at time t equal to 0, the fluid is at rest. It is set into motion when the plate suddenly starts moving with a speed v in the x direction. We show you in a schematic diagram in a while. Gravity acts in the z direction, but since the gravity acts downwards and we consider the rectangular coordinates always in the upward direction as a positive side, so we will say that gravity acts in minus z direction, negative z direction. We need to determine the pressure and velocity fields for this problem. So, in other words, by considering Navier-Stokes equation, we have posed the problem that it is a viscous Newtonian fluid. So the fluid is viscous, viscosity is there, and it is on top of an infinite flat plate. The plate is to move in the x direction with a velocity v suddenly. But when t is 0, everything is at rest. However, when this motion starts, then the motion starts due to an applied velocity in the x direction. The other forces acting is gravity, which as you always will be acting in the downward z direction. So we go for the solution, and as always, when a problem is posed, first of all, according to the problem, we have to consider what are the boundary conditions, what are the assumptions that we are taking. So what are our parameters? What are our limitations and what are not our limitations? And according to that, we decide what to choose and what to ignore. So the velocity and pressure fields are to be calculated for the fluid on top of an infinite plate that suddenly starts moving. The assumptions that we are making here are pretty obvious, but however, we list them down as we discussed. Whenever we are going to solve a problem, whenever we are going to attack a problem, we must write them down. We must list down the assumptions, the parameters, and the boundary conditions. And then we try to solve the four equations one by one. We have a continuity equation that we have to solve, and we have three momentum equations in x, y, z or z direction, which are known as momentum equations. So the first assumption is that the wall is infinite in the x direction and maybe in the y direction as well, but the motion is taking place in the x direction. Thus, nothing is special about any particular x or y location. The velocity is parallel everywhere, and therefore W is equal to 0. W equal to 0 means the W component, the velocity component in the z direction is 0, so there is no motion in the z direction. The pressure P is constant with respect to x. In other words, there is no applied pressure gradient pushing the flow in the x direction, and the flow is occurring only due to the viscous stresses that are caused by the plate that suddenly starts moving with a velocity v. The fluid is incompressible, so the density rho will be constant, and the fluid flow will have Newtonian properties. That means they will follow the Newton's law of motion, F is equal to ma, and the flow is therefore laminar, no turbulence is expected. The velocity field is two-dimensional in the xz plane, therefore v will be 0 and all partial derivatives with respect to y are 0. And gravity, finally, the gravity is acting in the downward direction. So this is the problem and assumptions associated with it. We will then, with these assumptions, we will try to move to solve this problem. At this stage, we have defined it, and we have also enumerated or listed the assumption, the conditions that are attached with the fluid flow model that we are trying to solve.